All right, so let's wrap up this problem. Of course, our goal here is still to determine V out of t, which is really just VL of t. We've got VL of s, so we need to take the inverse Laplace transform to get this expression back to the time domain. So let's just grab this and bring it on over there with us. I really didn't need an extra slide here. I probably could have gotten it all on one slide, but might as well use it. We can use this same Laplace transform pair that we used for the previous problem. And so what we see here is that my A in this expression is 1 over L over R, right? So I'm going to say VL of t is equal to 5 multiplied by e to the minus AT. The A is 1 over L over R, so it's going to be t over L over R times u of t. And this is basically a decaying exponential, which is exactly what we would expect from the RL circuit. If you remember correctly, RL circuit with a pulse or a step input, right? Initially, this voltage jumps up, and we expect this voltage to jump up as well so that the current remains 0 at that first instant in time. And then as the current begins to flow, right, this stays at something like 5 volts, and this starts bleeding off exponentially until there's 5 here, 0 here, and we have current flowing through the resistor and the inductor in series. And so that's exactly what this expression sort of demonstrates. And we can write it, of course, another way. We could write VL of t is equal to 5 e to the minus t over L over R volts from t for all t greater than or equal to 0, and that would allow us to drop the unit step function. Both are valid, and I think that it's really, hopefully you start to see that we kind of use, especially for these first order circuits, we use the same Laplace transform pairs frequently enough that you may start to memorize them. Even if you don't, you can always refer to the table. But nonetheless, you start to see how we play the game here. We take the circuit in the time domain, we write the expression in the time domain, we convert the expression to the S domain. This is that 4-step process that we saw already. I'm sort of doing it and just mashing all the steps together, but once we get it into an S domain expression that we can convert the last, we basically solve the algebraic equation for the quantity of interest. In this case, it's VL of S. Once we get VL of S, we take the Laplace inverse transform, or the inverse Laplace transform of that function of S, and we get a function of t. Our function of t is our final time domain expression, and that's how we solve the circuit. Okay, so this is the RL circuit example. We basically are almost through this module. We're almost through this class. I'm really excited that we only have one more section of material here, and we're going to wrap up this course pretty soon. So hopefully everybody feels like they're learning. If you have any questions, I know that this subject is not particularly easy. Please let me know. We will get them figured out. Iron out any misunderstanding that you have before the final exam. And I'm going to go ahead and wrap up this video. So we will see you guys in the next video.